Okay, so welcome back to class, everybody. I'd like to just begin by quickly reviewing what we did last time. And then I know many of you have questions on the homework assignment. That's going to be our first order of business today. But just quickly, what we did last time was we talked a little bit about stochastic gradient descent. In particular, we went through a proof that showed that we can use the gradient, the stochastic gradient, where we take the gradient and project on a uniformly random direction. And that's sort of sufficiently good for us to run the stochastic gradient descent algorithm. And if you missed that, it's on the video that I posted online over the weekend. We spent a significant amount of time going over homework 2, where you learned about things like deriving a class from a class that you hadn't written, from a class that somebody else wrote. You learned about various other things like writing a function inside of another function, which is sometimes quite useful, and we might use some of those later. And then towards the end of class, we almost completed a chi-square test for testing whether a uniformly random direction in the way that we talked about in class actually yields a uniformly random direction. Now, we didn't have time to complete that in class, but I did complete it on the video online. So if you're curious, you can go and look at the video, and it has the full code for that chi-square test. And I run it on both the two methods that we had talked about. So one was generating a uniformly random point in a square and then normalizing it. And the second was using a Gaussian and then normalizing it. And the Gaussian passes the chi-square test, but the square doesn't, which is sort of what we would expect. So the plan for today is to spend some time going over your questions on homework 3. So that's a significantly more difficult homework assignment than your previous ones. And that's how it's going to get as we kind of progress through the homework assignments. And in particular, one of the things that's going to happen is I'm going to give you less and less sort of hand-holding on the write-ups in terms of how to organize your code, right? So far I've been posting like build this class with these functions and these inputs and these outputs. And there's going to be less and less of that. So there's going to be a little of it on the next homework assignment. And after that, almost none at all. Like it's just going to be do this. And it's going to be up to you to organize your code in a way that makes sense. Because sort of thinking through that code organization, I think, is a key part of building reusable and understandable code. So I want you to get practice on that. And so as you're doing this assignment and the next one, think about how we do that, right? So, for example, the concept of an interface is really important in the homework assignment that you're completing now. So after that, we're going to introduce the next homework assignment. And that homework assignment is about implementing a large-scale machine learning algorithm on text classification problem. So we're going to go over the homework assignment. We're going to talk about how one uses stochastic gradient descent for large-scale machine learning problems, specifically in the way that we're going to do it in the homework assignment. And then in that homework assignment, I'm also going to have you do parallel computing. So what I mean by that is we're going to have this reasonably large data set, and you're going to split it over potentially multiple machines, but more often multiple processes on the same machine. And we're going to use an architecture where it doesn't matter. So it could be multiple machines, it could be the same machine, and the same code would work. So we're going to learn about how to use that architecture to sort of get a computation to run on potentially thousands of machines at once, which is really going to increase your computing power for a lot of data-intensive and computation-intensive problems. So now let's just begin with any of your questions on the current homework assignment. So you had, let me just go with Andrew because he said.
It was a pretty general question. When I'm trying to update the guess on the location of the minimum, it's coming out with 2 brackets instead of just 1 if you print that. And the way I'm getting that is then if you read that into the evaluation, it's giving me an error. And so the way I'm getting around that is I'm saying take and then just taking the indices.
So say again, you're taking the minimum.
So when I update x,
okay.
2x has 2 brackets on it.
Okay.
Instead of just 1. And
okay.
When you try to read that updated x into the evaluation of the function, I get an error.
Okay.
So the way I've been getting around that is just been like taking out those values using
Okay, so I roughly understand your question, and I think your question has to do with what's called in the assignment vectorizing your code. So I don't know if you've gotten to that part of it yet. But imagine a function that's sort of, I think one of the functions that we do is called doStep or something like that, right? So it takes in an x value and maybe like returns like the next x. Right. Okay, something like that. So one way I could write this function, so imagine that I'm solving a problem that's just in 2 dimensions, right? So this function might just take something like 0, 0, that's like 1 point, and return the next point. So maybe the next point here is 0, 1. Yeah. Right? So that's one thing that can happen. So that's what I would call non-vectorized version. So there's 1 point that goes in and 1 point that goes out of all these functions. But in the later part of the assignment, so I first kind of ask you to code it this way, and then I ask you to vectorize everything. Right. So when I say vectorize, what should be happening in these functions is this. You pass in something like 0, 0, and 0, 1, and 1, 0, and 2, 5. So I'm passing in a whole bunch of x values, like an array of x values. And what I'm getting out
is the next of all those ones.
That's right.
Right. And I've actually I've managed to do that pretty well as well.
So what you're calling extra brackets might be a function of this, right? So you may be passing this into a vectorized function. Okay. So if you pass something like this into a vectorized function, you might be getting an error that you don't know about, right? So you think that your code is sort of doing something, but it's doing something else. And so often in my code, what I'll do is a vectorized function will needs the shape of the array to be 2-dimensional, right? So I might write an if statement at the top of the function that does something like, if the shape of the array is 1-dimensional, in other words, some outside code called me like this, what I'm going to do is change that 1-dimensional array into a 2-dimensional one, and then execute the function.
Right, which I guess is basically what I'm doing using take.
So I don't do that using take. So I use take for things like finding the gradient. So sometimes that's useful. It helps me avoid some for loops there. So does that answer your question? I mean, other than debugging it, like one of the things I would do is %debug, right? And step through the code and see that at each line it's actually doing what you think it's doing, because most likely it's not. So other questions?
So with x0 with something like vectorizing would have 5 rows?
Say again?
On the vectorizing, would we be given x0 with 5 rows?
Yeah, so x0 is a sequence of points.
What's n data?
So n data is something that we're going to use. So you can ignore it here. We're going to use it on the next assignment. But it turns out that, so think about the parabola expressions that we have. They're expressed as a sum of a whole bunch of terms. So imagine that those terms are not like 50 or whatever, but there's like 8 billion of them. So one way to get a stochastic gradient is, instead of taking all 8 billion terms, is to take a random sample from those 8 billion terms. So n data is going to specify how large of a random sample we're going to take. But for this particular assignment, I think you can ignore it, and I think my code does indeed ignore it. But the reason it's there is because the way that I wrote my stochastic gradient descent code was actually so that it works with both this assignment and the next one. So that's kind of a remnant of my code being sort of more general than what this assignment's asking for. Other questions?
So in the first part, like you have asked us to define sgrad and then overwrite it in parabola, the derived class of parabola. So what's the difference between the two sgrads? I didn't quite understand what are we.
So we have two different ways of computing a stochastic gradient. So one is to pick a uniformly random coordinate and then return the gradient of that coordinate so that it's an expected, so that we have like an expected gradient. And then the second was to pick a uniformly random direction and then project the gradient in that direction.
So for the first case, but we have a point x, so we have to find the gradient at that point, right?
That's right. The stochastic gradient at that point.
The stochastic gradient at that point. So how do you pick a uniform random gradient? Like
how do you pick a uniform? So there's two different methods. We talked about them in class. I don't know if you remember. So one of them was to pick a uniformly random coordinate and then return the gradient only of that coordinate.
Oh, okay.
So that stochastic gradient is going to have zeros almost everywhere except one place where it's going to have a non-zero, right? So the other one is going to be computing the gradient and picking a uniformly random direction and doing the projection. That's right. And if you watch the resulting videos, like you can see that the algorithm works quite differently depending on which one we're using. Like the one that is picking a uniformly random coordinate is the video where the point is kind of always moving in the x or the y direction, right? And the other one is kind of bouncing around in all sorts of different directions before getting to towards the optimal.
So for the first description, you said that you just pick one like one dimension, and there you randomize to pick a uniform random coordinate. So how does this relate to your description that it returns the gradient of a uniformly random summand?
So if you look at the definition of a parabola, it's a sum of a bunch of terms. So a uniformly random summand is picking one of those terms and returning its gradient. And the reason I wrote it that way is because of exactly what I said earlier, that if you had like a sum of 6 billion things, like you're going to pick some of them and sort of return the gradient of just those things. And we're going to see that in the next homework assignment. That's exactly what we're going to do. So other questions? Yeah.
Actually, I have two questions.
Yeah.
The first one is about the first part, which is how we compute the stochastic gradient. And one of the two methods is we create a uniform random direction.
Yeah.
And we project the gradient in that direction.
Yeah.
But why do we need to do that if we have if we already have the gradient?
Oh, because I specifically want to build stochastic gradient descent, right? So it's in this assignment, the main reason for doing that is not computational. It's mostly to give you experience on creating some code and exercising your stochastic gradient code and making sure that it works with something where you know what the answer is, right? But in the next assignment, we're going to use it with a problem where you don't know what the answer is. And computing the gradient might force you to either run out of memory or might take too much computational power.
And the second question is in the second part, because it is an unconstrained problem, right?
Yeah.
So we don't need to project the yi into the physical set.
That's right. That's right. So what my code does for that projection is I have a function that's called something like identity projection. It takes in an x and it returns x. Right, so that's the function that I pass into my stochastic gradient code. But stochastic gradient code still calls a projection, right? It's just a projection that returns the same point that you are in. And so if you had a constraint problem, what you would do is you would change this function so that it actually computes a projection onto some constrained space.
Thank you.
Other questions? Yeah.
Well, okay, one question. There are some points where you start and the length of the next step is farther away than any minimizing direction can take.
So you start in a point that's too far away.
Like if you start at 3, 3, and the parabola centers at 0, 0.
Yep.
And the next step has to be 10 long. There's nowhere you can step that is of a lower evaluation than where you already are.
Oh, that's fine. Yeah, because stochastic gradient descent. So there's a group of algorithms that people call descent algorithms. And what they guarantee is that the function value is going to decrease at every step. Stochastic gradient descent does not do that. And that's because it's quite possible. Like, for example, let's say that my gradient is grad f, and what I add to it is nu, where nu is some sort of normal with mean 0 and variance like 10,000, right? So this is a stochastic gradient because its expectation is going to be 0, because when I take the expectation, the first part is a constant and the second part is 0. But a lot of the time, this is going to point in some place that's totally not a descent direction for this problem, right? And so so it's very possible that on your first step, you're going to get like an increase in the objective function value. But what guarantees that you eventually get to smaller and smaller values is the assumptions of the algorithm. So the assumptions of the algorithm are things like the step sizes being non-summable but square summable. And one thing that definitely led into a bug in my code and might lead into a bug in yours is the assumption that the gradient is bounded. Okay, so for a parabola, is the gradient bounded? Right, so if my parabola is alpha 1x squared plus alpha 2y squared, what's grad fxy? 2 alpha 1x, 2 alpha 2y. So is this bounded? Yeah, absolutely not, right? And so there's basically like only one way to solve this, or there's several. So one way to solve this is this. You add a projection function that bounds it, right? So if I'm always sort of like projecting to some box like between -5 and 5, then on that box this is guaranteed to be bounded, and then like everything's going to work just nice. Another thing which I did was I just do, or this is what my code does. So if like the norm of grad f is bigger than or equal to 10 or something like that. So I have a function that's called bound grad, and it takes in grad f and maybe some number like bound. So it checks if the gradient is bigger than the bound, and if it is, then grad f gets to be grad f over the norm of grad f times the bound. Right, so I changed the actual gradient magnitude, but not the direction. So it's important to not change the direction, but the magnitude has to be bounded, and that's one of the key assumptions that make the proof of the algorithm go through. Because otherwise, and this might be what your code is doing, which is that if you start at 3,3 and your step size is 10, your code is going to get to infinities like very quickly. Because what it does is it sort of bounces to 1010, it sees a huge gradient, and so even though the step size decreased, the gradient increased so much that it sort of overcame the decrease in the step size. And then it bounced over here, and it got an even bigger gradient. So even though the step size decreased again, it got an even bigger magnitude, and so it bounced over there. Does that make sense? Or I can draw it in terms of a picture. So here I am, and the first gradient sort of tells me to bounce here, right? And the second one, because now it's an even bigger steepness here, even though my step size decreased, because the step sizes are something like SI equals S0 over I to the gamma, right? So they're decreasing with every step. Like the increase here in terms of this steepness to that steepness overcomes this decrease. And so next time it sort of bounces up there. And now it's even steeper, right? And because of this bouncing around, it sort of diverges, and it doesn't actually converge to the optimal. So if you do this bounding, what it actually does is something like this. So this is my parabola, and it's essentially equivalent to sort of picking some points and saying that after those points, like that parabola sort of turns into a line, right? So like I'm sort of going to bound the gradient so that it doesn't get any steeper than this particular amount. And so now, because the gradient here is constant, even though at the first steps I might sort of bounce up quite a bit, eventually the decrease in step size is going to take me back down to 0.
So at some point the gradient value overcomes the step size.
That's right.
How it eventually does converge.
That's right. So at some point the step sizes sort of become smaller and smaller, and so they overcome any increases in the gradient, but only if the gradient is bounded.
Then on the first random not the random direction, but the random coordinate, where we get the gradient from that coordinate and go that way. If you, let's say you have a 3-dimensional array, so you could have either 3 of those coordinates come up. Will they all have the same length when you do your calculation?
So I have a 3-dimensional parabola. I picked a random coordinate. You're asking, is the gradient going to have the same magnitude?
The stochastic gradient.
So it depends on what point I'm evaluating, right? So if you look here, if I'm evaluating at the point 0.01, comma 10, right? So let's say this is x and this is y, and that's my gradient. And let's say both of the alphas are 1. Like the magnitude on the x direction is going to be like 0.02, but the magnitude in the y direction is going to be like 20. And so they're not going to have the same magnitude because it really depends on where you are. And so that you can also see in terms of the videos. So we have one parabola that's sort of non-symmetric in this way, right? And so what's going to happen is that in one of the coordinates, you're sort of going to get to the optimal value much faster than the other one. And that's if you plot the parabola, it's sort of like much steeper in one direction than in another. And so what happens is it sort of like goes to a valley and then takes that valley over to the optimal point. Other questions? Yeah.
Specific to Python. So, so while I was writing the parabola class and trying to, implement the f-evaluate function, if I put in a list as an input, the code that I've written doesn't work. So I need, maybe a numpy array. So how do you, like there could be different types of array. Like the one I use is numpy.array. So you could check in the code if it's numpy.ndArray. But there could be other array types defined in other packages. How do you, in general, check?
So in general, people don't. So typically, it's considered bad style to check for the type that gets passed in. So you might be used to that because of Java or C programming or something like that. But instead of doing that, just assume that that data type has certain properties associated with it. That way, anybody who implements those properties can use your function. Does that make sense? And so just assume it behaves like an array without checking. And it's up to the caller to sort of make sure that they pass in the right kind of object into there. Other questions? Okay, so great. And just kind of a general question from me, how are you guys doing on homework 3? Do you feel confident in completing it?
Yeah, it's a lot of work.
Absolutely, it's a lot of work. If you find yourselves, if I get sort of, so first, post on the discussion board if you have questions, right? So other people are going to answer your questions and help you sort of complete the homework assignment. And then second, if you all really need an extension to this homework assignment, you can let me know, okay? And we can sort of move the due date back a little bit, maybe to next Tuesday or something like that. But I think you can do it, and we have some other interesting things to do. So it's sort of worth continuing to finish that homework assignment, okay? Right. The next thing I want to talk about is we have an upcoming exam. So our first scheduled exam is, so it's the 20th right now. Our first scheduled exam is on the 4th. So if you recall at the beginning of class, I talked to you about how our first exam, or all of our exams, are going to be time-limited programming assignments, right? Where you get a problem and you have something like an hour and a half or 2 hours to turn in working code for that problem. So based on my past experience, because it's kind of a relatively unusual exam format, but also a really important one because that's how companies are going to interview you. It's useful to do some practice exams beforehand, okay? And so the way that we're going to do the practice exam is I'm going to pick a time on Canvas, and we can sort of maybe discuss right now and sort of pick a good time to do it. I think we should do it next week. And what's going to happen is there's going to be an assignment, in quotes. It's really going to be the practice exam, right? That's going to come out at a particular time. You're going to have 2 hours to complete it, and you have to turn it in by the end of those 2 hours, and then it sort of disappears. Like, you can't turn it in anymore. And that's how the actual exam is going to work. And the same as the practice exam, the actual exam you can take anywhere. Like, you don't have to be in this room. Like, you could be at home. You could be in the library, like wherever you want. It's open internet, open everything. The only thing it's not open is your friend or anybody else, right? Like, you can't talk to anybody to actually complete that exam. And so just to kind of get prepared for the practice exam, what are convenient times of the week next week for you all to do a practice exam? It's going to take about 2 hours, and my suggestion is that we do it some evening time, just because most people are going to have that time available.
Could you make a few iterations of it?
So I do have several practice exams, if that's what you mean.
Well, just it seems like people could take it any day of the week that made sense for them.
I see. So another option is for me to just post it, and then for you all to time yourselves, right? Which would also be perfectly fine. The only thing that you would be missing is sort of the aspect of like turning it in on Canvas within the 2 hour time period. So I would say, time yourselves and give yourselves like whatever, 10 minutes to figure that out. You probably don't need 10 minutes, probably like more like 5. But let's do that. I'll just post the exam online, probably on Canvas, and then all of you guys can time yourselves. And it's going to be 2 hours. So it's a 2 hour time limit, and it's going to be the same for the in-class exam. So we go until 4:45 usually, and so you're going to have sort of a full 2 hours instead of an hour and a half or whatever the class is scheduled for. Okay?
It'll be 3:30 to 5:30.
Yeah, 3:30 to 5:30 on the 4th. Okay? So any questions or discussions about that? Okay, so next I'd like to talk a little bit about our next homework assignment. Say again? Great. Okay, so in the next homework assignment, so in this homework assignment, you're just kind of implementing stochastic gradient descent. You're getting used to vectorizing code so you can process multiple points at once. But in the next homework assignment, we're going to actually use it for something useful. And so in this homework assignment, what you'll learn about is large-scale machine learning problems, building parallel code and executing it on multiple machines, and working with a distributed database. So you're going to actually build a distributed database and use that database to execute stochastic gradient descent for a machine learning problem. So let's understand a little bit what the problem looks like. And to do that, I have to introduce you to a couple of Python packages, which I've mentioned a couple of class periods ago, but I have not yet shown you in practice. And those packages are Pickle, and shells. And another useful one is Gzip. Okay, so one of the things that you might find yourself wanting often is, suppose that you're working on some interpreter session, and you've sort of built some code, but then you've typed in some more functions, and you've gotten the data to a really nice point, right? You've run a bunch of experiments. They took a lot of computation. You don't want to rerun them, and what you want to do is save the results. So that's what the Pickle module does. So the Pickle module basically, sometimes people call it serialization. What it does is it turns objects into strings. So let me maybe just show you from an example instead of looking at the documentation. So there are two versions of the Pickle module. So one is cpickle, spelled like this, and the other is pickle. The only difference between them is that cpickle is a little faster. So generally, I'd suggest using cpickle. So let's say that I have something like, let's say a tuple is just some tuple 4, 5, 6. And that's the piece of data that I want to save. So one function in cpickle is dump s, okay? And then in here, I can pass in a tuple. And what it does is it turns that tuple into a string that's not human readable, but is machine readable, okay? So you could take this string and email it to your friend, and then your friend could do cpickle.load from string, and then pass in this string. And out's going to come the tuple that you passed in. Does that make sense? So almost any object in Python you can do this with. There are some that you can't. So if you start building really complicated objects that, for example, have functions that are sort of created at runtime that are stuck onto the object, those you might have trouble pickling. But any of the basic objects like pandas data frame, SciPy array, dictionary, like anything like that you can pickle. So other ones that are useful are, so dump s sort of dumps it into a string, but you could also just do dump, which lets you write it out to a file, right? So you could take the object and write it out to a file, and this file has to be a file handle. So you would do something like cpickle dump this a tuple into something like mydata.pickle. Okay, so the second argument here, I said open a file mydata.pickle for writing, okay, and put this tuple in there. So now let's say that I close everything here, look at all the files that I have, and one of the files that I have here is mydata.pickle, okay? So then I can open up IPython the next time that I'm doing things, import cpickle, and just do cpickle load open mydata.pickle. And now it's going to come my tuple that I stored in there. Make sense? So really, really useful. And a slightly better interface to that is shelves. Okay? So shelf just looks like, so it manages, the description is manage shelves of pickled objects. So a shelf is a persistent dictionary-like object. So essentially what this does is it creates a dictionary that's on disk, okay? So I could do, let's say sh equals shelf.open myshelf.dat or something like that. And then I could do shelf.fred equals Joe, right? So this just behaves like a dictionary. Shelf.t equals 2, 3. And then I could do shelf close, and it closes all of that, and then maybe like exit. So now when I look at my files, I have the myshelf.dat right there. And so next time that I start up Ipython, I could do import shelves, and then ds equals shelf.open myshelf.dat. And then if I look at ds, it has all the stuff that I wrote in there. Does that make sense? So this is actually using Pickle in the background, right? So every time that this dictionary gets a key value pair, it sort of pickles those things and sticks it in that file in a way that Shelf can read it. Okay? I find both of these tremendously useful, especially for long-term research projects where I need to save data that I've computed. So the reason I'm introducing them is because for our next problem, for our next homework assignment, we're going to use a data set called MNIST. So that's this data set. And you're going to download it in a pickled Gzip format. Okay? So this uses the Pickle module to sort of store it on disk, but that's just a big string. And so that big string is sort of takes up too much space, so we want to zip it. So it's both pickled and Gzip. And some other useful modules in Python are the Gzip module, and there's an equivalent one for zip that just lets you read and write Gzip files without unzipping them first. Okay, so let's just load this MNIST data set as follows. So I'm going to import cpickle. And then I'm going to import Gzip. And I'm going to say that the data set is cpickle load Gzip open MNIST. Right, so the only reason that I didn't do open and I did Gzip open is because this thing is zipped. And so I need to pass it through an unzipper before I can read it. Okay, so it takes a while because it's a reasonably large data set. And if you look at it, it turns out to be a tuple of 3 things. Okay, so ds sub 0 is these are images actually. So they're presented as SciPy arrays, but each one of these rows is an image, and each image corresponds to a handwritten digit. Okay, so this first image kind of looks like this. So that's the first image. When you read it from the file, it's just like an array, right? And the array is just giving you all the pixel values across the screen here. And on the bottom is the actual handwritten digit that that image corresponds to. So same with the next one and the next one and the next one. And the first part of the data set, that's called the training part of the data set. So there's 50,000 of these images in the data set, and each has a dimension of 784, because there's 784 pixels in the image. Okay. What we're going to do is we're going to write some machine learning code that is able to take in this array, basically it takes in the image, and then tries to produce the digit that corresponds to that image. And you're going to use your stochastic gradient descent code to do that. Like you're basically going to be building the code to do all of this yourself, sort of building on the homework assignment from last time. Okay? So let's talk a little bit about how one might go about doing this. But before that, so I said this data set is split into 3 sections. So the first one is training, that's 50,000, that has 50,000 images. The second one they call testing, it has 10,000 additional images. And the third one they call validation, which has another 10,000 additional images. Okay, we're primarily going to work with the first one. So we're going to do all of our computations with the first one, all of like finding various parameters for whatever function we're going to optimize. and then we're going to use the other ones to see if what we're doing actually works. Okay. Okay, so let's discuss how one might go about taking an array of these numbers and producing the actual digit that corresponds to those numbers. And to do that, we're going to build a multi-class classifier. Okay, so I have to introduce you to some basic machine learning terms. And these are useful to know, and it's one of the reasons why I picked this homework assignment. Because quite often, you'll be asked these terms in interviews, okay? So a classifier basically takes some data, let's call it xi, and maps it to 0, 1, okay? So it's like a category. So imagine that, so one way that you could take our problem and turn it into a classification problem is, instead of asking you which digit is it, I might be asking you, is it a 0 or is it not a 0, okay? And so if it's a 0, maybe you output 1, and if it's not a 0, you output 0. That's like a classification problem. So split the input data into these two categories, okay? We have a multi-class classifier, which is very similar to a classifier, except instead of 2 categories, we might have how many ever. And in this particular case, how many categories do we have? 10, 1 for each digit, right? So the general problem here is you get xi and you have to put it in the right category. So for the assignment, we're doing this in terms of images because it's kind of nice. It lets us plot things. It lets us visualize the results. But it's the exact same problem for almost, for like a large section of machine learning problems. So imagine that you work for a hospital and you're trying to take in some patient's data and figure out what kind of disease this person might have, right? So you might build a multi-class classifier where the categories are potential different diseases, and the xi values are sort of readings from various tests that the patient has gone through, and you have to take those readings and put it into the right category. So let's talk about how we're going to do that. Okay, so here I've given you some more discussion on organizing your code, like building a classifier base and so forth. So I'm going to skip this. You can read this on your own. There's reasonably a lot of text on it. But let's actually talk about the different kinds of classifiers. Okay, so in this homework assignment, I'm going to have you implement 2 different kinds of classifiers. So the first is called a k-means classifier, and the second one is called a multinomial logistic classifier. And in general, the way that a classifier works is that it has what people often refer to as a loss function, and it tries to find parameters that minimize this loss function on your input training data set, okay? So just to visualize this, it's like whatever function of some parameters. So here I call them W0 through W9, and there's one set of parameters associated with each category. So W0 are all the parameters with category 0, W1 are all the parameters with the 1s, and W9 are all the parameters with the 9s, okay? And data set is my whole data set of all like 50,000 images and their labels, okay? So I'm going to try to learn what are the right parameters based on this data set. And the way that classifiers often do this is by minimizing some objective function, okay? So the objective function that a k-means classifier is going to do is the following. So let me just increase the font size here. Okay, so the WI are the parameters for the ith category. And consider a specific image, right? So this is the kth image, like the 5 that we saw, that's the first image. So AK is the data for that image. It's that whole big long vector. That's all of the pixel values for the image. And BK is its category, which is the 5, okay? Like I know it's in the 5th category. So the loss function for this is to, let's consider just the first image, that's that 5. Is I'm going to have as many W's as there are pixels in the image, right? So there were something like 784 pixels in the image. So each of my W's, like W0 is going to have 784 values to it. W1 is going to have 784 values to it, and so forth. So what I'm going to do is take the W's for the 5th category and subtract from that the image vector, okay? And I'm going to take the norm of that squared. And so let's think about this objective function. So if you iterate over all 50,000 images, for each image, I get that particular W and then subtract that particular image's data. Does that make sense? And the objective function is the sum of all of that.
Where do the W's come from?
So the W's are parameters that we're going to try to optimize. Okay, so we're going to try to find what are the right W's by minimizing this. That's right. That's right. And in fact, we're going to use your stochastic gradient descent code to figure out what the W's should be. Okay, so the idea, so this might look a little bit weird for you, but here's the idea behind this classifier. So there's a WI, like there's a W0, there's a W1, and that kind of specifies the center of that category in 784 dimensional space, okay? And what we're doing, if you think about minimizing this, is we're trying to find the W that minimizes the distance from all the 5s that we've seen, right? And we're trying to find a W0 that minimizes the distance from all the 0s that we've seen. A W9 that minimizes the distance from all the 9s that we've seen, and so forth. Does that make sense? And so you're going to write stochastic gradient descent. So you're going to subclass this classifier base class that I have you write. You're going to write some gradient functions on it. And in particular, the things that you're going to write for it are classify, funkyval, and gradival. Okay, there's only 3 things that you need to write for a classifier. Evaluate the objective function, classify using the objective function, and evaluate the gradient. So classify, so imagine that I've minimized this, okay? So you gave me 50,000 examples, and I've minimized, I found the W's that minimize the distances. And now somebody comes along and gives me a new image, okay? Which category are you going to put that image in?
Compared to all your W's and see which W is close.
Exactly. The one that's, so I'm going to put it in the category that has the closest W. Exactly, right? So that's what the classify function here does. So you have a bunch of parameters that are your W's, and it's going to return the category that's closest to the input value. Funkyval does this, and gradival evaluates the gradient of this. So now you guys were asking me, what's the point of n data? Well, I hope that now you can see what the point of n data is, right? So imagine that you had to evaluate the gradient here. About how long would it take? So DS, our data set, has 50,000 images in it, and each image has 784 coordinates. It would take a long time. I mean, it's not going to be super slow, but it would be reasonably slow, right? And so instead of evaluating it on the whole data set, what we're going to do is, instead of taking the gradient of this sum, we're going to pick a uniformly random sample of the data set and evaluate it on that sample. So if n data is something like 300, instead of doing it on 50,000 images, I'm going to evaluate the gradient on 300 images. Make sense? And the next time that I call sgrad, I'm going to evaluate it on a different set of uniformly randomly chosen 300 images, and so forth. Okay, so some useful things for you here is just to help you debug. This is what the gradient looks like for the third W's, for W3, evaluated at 0, okay, for that classifier. So it's the squared loss gradient for the third category and the first 50 data points evaluated at 0. So when I say the first 50 data points, I mean the first 50 images. Because depending on which images I pick, I'm going to get a different gradient. So any idea why the gradient would look like this on the first 50 images? I mean, it's somewhat surprising, right? Like you might imagine, oh, it sort of has an arbitrary sort of shape to it. Well, it's evaluated at 0. Keep that in mind. So what does this gradient look like if I look back at this function? So what does this gradient look like? That's right. Okay, so it's going to be 2 times this, right? And evaluated at 0, I'm just going to get 2 times the sum of the A's. So the gradient here is like almost like an average of the first 50 images, okay? And in fact, when you
Is the first 53?
That's right. It's the first 53. So why is it the first 53s? Or it's the 3s within the first 50 images. It's not the first 53s. It's the 3s within the first 50 image. So why is it the 3s within the first 50 images? Because where does W3 appear? In which of these summands?
Just the ones that are already classified.
Yeah, just the ones that have 3s as an image, right? Because W5 goes with the 5s, W9 goes with the 9s, and so forth. Okay? Make sense? Okay, so that's our first classifier. And let's talk about our second classifier. So this classifier works by assigning a probability to each category. So the first one was kind of based on distances, right? So the idea was kind of pick a W that's close in 784 dimensional space to all of your 3s. So here we're going to assign a probability to each category. So the probability that we're going to assign to the ith category is Wi dot A over the sum of over all the categories, and this should really be a J, of Wj of e to that. Does that make sense? So I've sort of assigned a weight to each category. So somebody gives me data point A, and how am I going to classify it? I'm going to pick the category that has the largest probability associated with it. And each category has this numerator and this sum of all the numerators as a denominator. Does that make sense? Okay, so that's the category that's how I'm going to assign probabilities to the category. So let's think about this classifier's objective function. So this classifier is going to want to maximize over all the W's the likelihood of the observed data, right? So you give me a data set of 50,000 images. So what I'm going to want to do is maximize the product from 1 to 50,000 of the probabilities of all of those, of seeing all of those matchups between that category and that piece of data. Does that make sense? So very, very similar as the previous one, just the previous one was a sum and a min and so forth. This one's a product and a max, right? Now, unfortunately, our stochastic gradient descent code only works with minimizing functions, right? Like that's how we wrote it. And so we want to transform this into a function minimization. So let's do a couple of transformations. And some of you may have seen these before. So we'll start with this function that we want to maximize, which is just a copy of that. And the first thing we're going to do is take a log of this function. Now, why can I take a log of the function and it doesn't change the argument that maximizes it? That's right, because log is increasing, right? Because log is increasing, I can take logs here, and it's not going to change the output W. So this is not quite right because the values are not equal, but the optimizing locations are equal, right? Okay, so when I take logs, this just becomes WBK times AK, and this becomes log of the sum of all of this stuff, right? And then the next thing that we're going to do is we're just going to take a minus sign on the inside and the outside, which is going to flip our max to a min, okay? So now I have something that you can stick into your stochastic gradient descent code, okay? Now this thing's gradient is much more complicated than the previous one. In particular, to find the gradient, you sort of have to think carefully about these expressions, and I'm going to let you think about it a little bit, okay? So we're not going to do it in class unless you ask me a question next week or whenever you've had some time to work on this homework assignment. But you can do it, and it will be useful. So similarly, this is what the gradient looks like for the fourth category and the first 30 data points of the data set. So again, you might think that this gradient's going to look like whatever it looks like, but it has a very particular shape. So this is the fourth category, so it's trying to recognize 4s. So as you can see, there's kind of a 4 here. And the reason that this is sort of looks like this is because if you see any pixel values that are up here, then it's probably not a 4. Like it might be a 9 or something like that, right? So it's saying these should not be pixels that are on. These should not be pixels that are on. But if these pixels are on, I'm sort of more confident that this is a 4, right? So that's how you could interpret this gradient. And in the homework assignment, I'm going to lead you through sort of building these plots. And I very much encourage you to sort of play around with them. It's going to give you a lot more intuition about how these algorithms work than anything that I could write on my tablet or really say to you verbally, okay? So the next bit that you're going to do is you're going to test your classifiers with your stochastic gradient descent code. So for me, when I wrote it, and maybe you're going to get different results, but for the k-means classifier, I'm getting about a 17% error, and it took me about 50 seconds to run 3,000 iterations of stochastic gradient descent, okay? So just with that simple k-means classifier that you guys could probably, thinking carefully, implement in a day or two, you could get over 80% accuracy in classifying these handwritten digits, okay? With the multinomial regression one, or a multinomial logistic one, I got an error of just under 10%, okay? And it took significantly longer. And the main reason for this is because gradient is a lot more expensive of a computation for that one than the previous one, okay? So the next thing we're going to do in this homework assignment, and I haven't shown you how to do this, that's sort of next on our list of things to do, is we're going to parallelize things. So this data set, even though it seems like 50,000 is reasonably large, on a company like, let's say, Google or any web-based company, your training data set might be 7 billion examples, okay? And there is no way that those 7 billion examples are going to fit in the memory of your one machine. And so what we're going to do in this part of the assignment is kind of simulate an environment where we have a large database, and we're using that distributed database to actually do the stochastic gradient computation. So in particular, we're going to take those 50,000 examples, and we're going to put a chunk here, put a chunk here, put a chunk here, put a chunk here. And then when you compute stochastic gradient, we're going to sort of sample from each one of the chunks of data separately and in parallel to do the gradient computations in a distributed way, and then put them together to actually do stochastic gradient descent. Okay? So I'm going to show you a little bit about how to use parallelization in Python in a moment. But just to show you some differences, this is the same example with multinomial logistic classifier, and it took maybe about 40 seconds less time on my laptop. Okay, and this is going to be way, way, way faster on larger examples, and especially if you have even more data points that you want to run stochastic gradient descent on. Okay, so any sort of questions about the overview of the assignment and where we're headed? Okay, so my plan generally is if we don't move the assignment that you're doing right now back any, that your current assignment is due on Thursday. That's when you're going to get this one. And this one's not going to be due until after the exam. So you're going to have plenty of time to do it. But of course, in the middle, we're going to be doing things like practice exams and various other things. And so it's not like you're not going to be busy with other stuff either, right? Yeah, I agree. And personally, I find this assignment more interesting than the other one. The main reason that I split it in two is, one, to sort of give you a breather. I was thinking about putting these assignments together into one big assignment. But one was to give you a breather. Two was to give you a chance to debug your stochastic gradient descent code. Because the idea with this one is that you should be able to use your code from the previous assignment to actually implement these classifiers. Okay? And so one of the goals is to give you the idea of building reusable code, right? So this way, you have one research project, you built something. For the next one, you can reuse what you built from your last one, okay? Okay, so let's talk a little bit then about parallelizing things in Python. Okay, so there are many frameworks that allow you to do parallel computing in Python. So the general idea behind parallel computing is that we're going to have these processes that are running on many machines, or potentially multiple processes on the same machine, and they're going to be communicating with each other, right? So one process might go to the other process and say, hey, can you compute this for me? That process goes and computes something and then returns the answer back. So let me give you sort of a picture view of what this might look like for computing stochastic gradient descent. So imagine that we've put a piece of our data here, a piece of our database here, a piece of our database here, and one here, and one here, right? And this is our stochastic gradient descent code. So imagine that each of these boxes is running on a separate computer. For this assignment, you're probably going to run them all on your computer, but your computer also has multiple processors, right? And that's why I got the speed up when I ran it in a parallel version versus not, because my computer was actually using its multiple processors to compute stochastic gradient descent. So what stochastic gradient descent code is going to do is it's going to want to compute gradient, right? And let's say that it does compute gradient with n data equal to 300. But what it might do is maybe there's 30 data points from there, there's 50 data points from there, 100 data points from there, and the rest from there. So it sends those numbers to each of these different machines. And each of those machines itself kind of samples a uniformly random sample of 100, a uniformly random sample of 50, of 30, and so forth. and then uses those uniformly random samples to compute a gradient, and then returns all those gradients get returned here. Does that make sense? And then this program then takes a step of stochastic gradient descent and then computes another gradient and asks those guys to compute some gradients for it. So the whole computation is happening on many, many machines at once. Okay. So you may have heard of Mapreduce. So how many of you have heard of Mapreduce before? So that's kind of a very common framework of parallelization. And it works not very differently than what we have on the board here. So we have our distributed database, that's all of these pieces. And that's what people call the mappers. Okay. So what are they mapping? They're mapping this database to a gradient. Okay. So each of them sort of got a number like give me 50, give me 100, give me 30. And they use their local database to map that database to a gradient that uses that many data points. And then sends it to this guy, which is the reducer. Okay? So the reducer takes all those gradients, sums them together, does some extra computations, does like a gradient step, and then maybe calls another map operation on the mappers. Okay? So that's the basic idea. So the module or the method that we're going to use in Python to do this is called Ipython.Parallel. And it's very well documented online. So maybe we can just look at some quick examples. So I'm going to teach you these various interfaces, but this is how you start all of the processes that are going to have the various pieces of the data on them. So you call IP cluster start N4. So that means start a cluster that has 4 what is called in this particular framework engines. Okay. So let me just do that. Okay, and it's going to output some things like starting IP cluster, creating a PID file, starting a controller, and starting the engines. So in terms of a picture, the way this works is like this. These are the engines, and each of them have a number, like engine 0, engine 1, engine 2, engine 3. And there's something called the controller. And there's another program here called the client. Okay. So what's the SGD code is actually going to run into the run on the client, and the controller is just a tool to communicate between the client and the engines. Okay. So whenever these requests and answers go out and come back, it's the controller that's kind of managing all of that communication between everything. Okay, so when we do this, so let's execute this code. And it's going to be documented here, and I'll post this online as well as you have, so that you have it. So we're going to so I imported the parallel module up here, and then down here I created a client. So at this step is when this program connects to the controller and learns about how many engines there are there. Okay. So now let's see what we can do with this client object. Okay. So if you do C dot, one of the things that it does is you could look at c.ids, okay? So those are the IDs associated with each of the engines. Because I did IP cluster 4, there's engine 0, engine 1, engine 2, and engine 3. Okay, make sense?
Where did you run the IP cluster thing?
I ran it from the command line.
So it will be different for different terminals, right?
That's right. So you have to figure out how to run it in Windows. On a Mac, it's probably very similar to what I did. You just write IP cluster start N4. Okay, so those are our IDs. And so one of the things that you can do is create a direct view, or what this architecture calls a direct view. So a direct view allows you to send commands to the engines. And so one of the things, so you can think of each of the engines as running a little Ipython interpreter inside of it, okay? So when I did that IP cluster start N4, what I actually did was start 4 Ipython interpreters. So one of the things I could do is something like this: dv execute import scipy. So let's run that. So it returns asynchronous result object. So what that means is that the client program is not going to wait for the answers from the engines before it continues. Okay. And in general, if you look at the documentation for execute, there's an option here called block. Okay. So by default, it's false. But you can also pass block equals true, and that basically means, should I wait for the answers from this request that I'm making? So the client here made a request to all the engines to import scipy, but it did not wait for the answers. Okay? So let's do something else with our direct view interface. So yeah.
So if we didn't wait for the answers, so it might happen that the engines haven't imported scipy and we have started executing things.
Oh, that's right. And oftentimes you actually don't want to wait for the answers because the client has some other stuff to do while the engines are sort of doing their complicated long computations.
But that could raise an error too, right?
Oh yeah, absolutely. And debugging parallel code is significantly more difficult than debugging serial code for exactly the reason that you said, which is that sometimes if you're getting a error on the engine, it's somewhat difficult to find out what it is. Now, fortunately, with this parallel, so let's try something else. Give me 1 second, sorry. So let's just import let's import a module that shouldn't exist. Okay, so I should get an error here. And what did I actually get? I actually got 4 errors. Okay, and that's because whoever implemented this scipy or Ipython parallel interface did a really good job at it. Okay, because what happened was there was an exception thrown at the engine that got communicated to the controller, and then the controller communicated it to the client. Okay, but in general, on most other parallel computing interfaces, you would not have this ability. Okay, so here you get a little bit of feedback, but not nearly as much as when you're writing serial code. Okay, so maybe it's a reasonable place to end class here for today. Next time we're going to pick up with continuing to discuss parallel computation in Python, and also going over the homework assignment, because I didn't hear any complaints from you in terms of finishing it by Thursday. Okay? So I'll see you all next time, and thanks a lot for listening.